Hello friends, welcome to lecture series on essential mathematics for machine learning. Now, if the two classes are not linearly separable, then how can you find out an optimal separating hyperplane, at least which is best suited? If they are not linearly separable, at least we can find out a hyperplane which is best suited. So, how can we find that? Now, we have two classes. See, in this figure you are having two classes. This is +1 class, which is this hollow circles, and which is a dark circles, these are of -1 class. Okay. Now, one pattern from this class is in this class and one pattern from this class is in this class, suppose. So, of course, these two classes are not linearly separable. So, of course, they are actually non-linearly separable. But if we are interested to find out a hyperplane, the best fitted hyperplane which can separate these two, so how can you find? So, in this case we will find misclassification error. We will find misclassification error corresponding to all the patterns, okay, all the patterns of +1 class and -1 class. The patterns which are correctly classified, for those patterns misclassification error will automatically be 0, and those patterns which are not correctly classified or which are misclassified, for that we will try to minimize the misclassification error. So, now our objectives are two are our objectives. The one is we have to maximize the margin, which is nothing but minimization of norm W square by 2 or 1 by 2 W transpose W, or second is we have to minimize the sum of misclassification errors. Okay. So, we have two objectives. Now, how can we model corresponding optimization model? So, let us see. So, suppose the patterns are not linearly separable, then the error minimizing LPP will not have a 0 objective value. That is, in the optimal solution of the minimizing LPP, all error variables are not 0. Let these error variables be denoted by xi I, okay, I from 1 to m for all the patterns. Now, we have to find out a classifier for which the total error is least, which is the sum of xi I, and the margin is maximum. So, now the equivalent optimization problem will be 1 by 2 W transpose W, which is the minimization of norm square W upon 2 plus C times summation I from 1 to m xi I, subject to this constraint. We are adding xi I here. In the hard margin classifier we are not dealing with xi I, because all misclassification errors are 0 there, they are linearly separable. So, we are adding xi I and that is greater than or equal to 1. So, and xi I are non-negative, I from 1 to m. Now, what is this C? This C is a free parameter which is greater than 0, is a scalar and it is greater than 0. So, what is the importance of writing this C? See, here we are having two objectives. The one objective is to maximize the margin, the other objective is to minimize the misclassification error, the sum of misclassification error. Basically, it is bi-objective. So, we are trying to make a single objective problem by adding this C. If this weightage, if this C is very small, that means we are giving less preference to the misclassification error and we are giving more preference to the margin. That means the margin will be maximum, but the patterns may not be, all the patterns may not be correctly classified. However, if we are giving C a large value, that means the larger value of C implies that we are giving more weightage to the misclassification error than giving weightage to margin. So, basically it depends at which C we take, okay, it depends on the decision maker. So, usually we take C as 1, so that we give equal weightage to both the objectives, margin as well as misclassification error. So, this I have already discussed the importance and the implication of C. Now, what is the Lagrangian of this function, this problem? As we see in hard margin classifier, we can construct a problem and we can solve that problem using KKT conditions or using finding the dual of the given problem. In the same way, here in soft margin classifier also we can find out the Lagrange function, hence the KKT conditions, and hence we can construct the dual of a problem which will make the problem computationally easy. So, what is the Lagrange of this problem? Let us write the problem first. What is the problem? Soft margin classifier, what is the problem? It is minimization of 1 by W, 1 by 2 W transpose W plus C times summation I from 1 to m xi I. Okay. Subject to what are the conditions? Conditions are di W transpose xi minus 1 plus xi I is greater than or equal to 1 and xi I non-negative for all I, for all I and for all I. So, this is our problem. Okay. Now, first let us define the Lagrange of this problem. The Lagrange of this function will be, this problem will be given by 1 by 2 W transpose W plus C times summation I from 1 to m xi I, then it is plus alpha I, the sum of alpha I over I, okay. It is 1 minus di W transpose xi minus 1 minus xi I, and it is minus beta I xi I, okay. It must be sum over I, okay. So, now we can write it is di W transpose xi, it is minus b, it is minus b, okay. As we have seen here, it is minus b. So, minus b will come here, okay. Now, this is the Lagrange of this problem. So, we will write the KKT conditions as we first take gradient of W L equal to 0, and this implies if we take the gradient with respect to W. So, what this gives? It is W, from here we get W, no term of W, so it is 0. So, from here we will get minus summation over I alpha I di W equal to 0. So, this implies W equal to summation over I. So, it is we are differentiating with respect to W. So, it is xi, sorry, it is xi. So, it is alpha I di xi, okay. So, this is the first KKT condition. The second is del L by del B equal to 0. So, this implies when you differentiate with respect to B. So, that will be summation alpha I B I alpha I d I, it is d I over I is equal to 0. So, the second condition. Now, we differentiate with respect to xi I, del L upon del xi I equal to 0. So, that implies C minus alpha I minus beta I equal to 0. So, these are the conditions for all I, of course, and of course, this alpha I times 1 minus d I W transpose xi minus b minus xi I is equal to 0. Alpha I must be non-negative for all I, and xi I must be non-negative for all I. So, and of course, feasibility conditions must be maintained. So, these are the various KKT conditions which we can obtain using the Lagrange function of the given problem. So, these are the KKT conditions which I have just obtained. So, one more condition is beta is xi equal to 0, which can also be obtained because beta is a Lagrange multiplier corresponding to this constraint xi. So, beta is xi must be 0 for all I, plus feasibility conditions. Now, let us try to analyze these conditions. See, if you see 3 and 6, it is C minus alpha I minus beta equal to 0. Okay. So, from here it is C I minus alpha I times xi I equal to 0. So, let us see how we are obtaining this condition. So, from this it is so this is easy to obtain. You see what is beta I from here? Beta I is C minus alpha I. So, you can substitute beta I here. So, it is C minus alpha I times I equal to 0. So, we will get this condition. Now, from this condition the following cases we may obtain. What are the cases? Now, first of all, since alpha i's are non-negative, alpha i's and beta i's are non-negative. So, that means this alpha is between 0 and C only, because beta I is non-negative, alpha I is non-negative. So, that means this alpha I is between 0 and C only, it cannot be more than C. Okay. If it is more than C, so then beta I will become negative, but it is non-negative. Okay. So, the first condition which may arise, that this alpha I is between 0 and C. If alpha I is between 0 and C, that means this term is non-zero. This term is non-zero, that means xi I equal to 0. If xi I equal to 0, that means that pattern is correctly classified. If we come to equation number 5, from this equation number 5, this alpha I is non-zero, xi I equal to 0. So, that means 1 is equal to this, 1 equal to di w transpose xi minus b. That means that particular pattern belongs to the bounding, that belongs to the hyperplane. Okay. That means point xi lies on the bounding planes. Okay. Since it lies on the bounding planes, that and such patterns are called free support vector. Okay. So, what I want to say, that if alpha is between 0 and C, then the pattern is correctly classified and that pattern will lie on the bounding plane itself, and such patterns are called free support vectors. Now, the second case, suppose alpha is equal to 0. If alpha equal to 0, again C is non-zero, so xi I will be 0. So, xi I will be 0, that means the pattern is correctly classified. Okay. Now, from 4, now come to equation number 4. So, from this equation 4, xi I is 0. So, that means this is less than or equal to minus 1. So, that does not lie on the bounding hyperplane, but lies on the correct side. If it is in a positive pattern, lies on the positive side, if it is negative pattern, lies on the negative side. So, if alpha equal to 0, that means this condition is satisfied. Here equality is satisfied, however, here it is less than or equal to. Okay. Now, the third case left, when alpha is C itself, it may be C also, but it cannot be more than C. If alpha equal to C, then we are having two cases based on xi I. So, if alpha equal to C, then beta will be 0. From here you can see, if alpha equal to C, then from this equation beta I will be 0. Okay. And from 5 what we obtain, from this equation 5 what we obtain. So, alpha I is C, so which is non-zero. So, from this equation we will obtain that this expression is nothing but 1 minus xi I. So, this expression is nothing but 1 minus xi I. Now, if this xi I is between 0 and 1, so what does it mean? If it is between 0 and 1, this means this is positive. This is positive means the pattern is correctly classified, because it satisfies this inequality. So, that means the pattern is correctly classified and lies in the dead zone. Okay. But if it is more than 1, so this is negative. This negative means this inequality reversed, that means the pattern is not correctly classified. Okay. So, such pattern xi where alpha I equal to C, these are called bounded support vectors. Okay. Now, let us try to understand this by this figure. We are having here two classes, one is denoted by star and other are denoted by bold circles. So, we are having 1, 2, 3, 4, 5, 6, 7, 8 patterns, 4 from pattern of star and 4 from pattern of bold circles. Now, suppose we are studying this pattern 1. Now, for this pattern 1, since this lies on the correct side, because this we are denoting by, this side we are denoting by star, I mean suppose it is plus 1 class, and suppose it is minus 1 class, and this side is suppose plus 1 class. So, the patterns of the star are basically minus 1 class and patterns of bold circles are from plus 1 class. So, if we are taking the first point, So, that means it is correctly classified, okay, and correctly classified. So, that means xi 1 equal to 0, xi for this pattern will be 0. And what we can say about alpha for this pattern? See here alpha for this pattern will be 0. If it lies on the bounding planes, then alpha will be between 0 and c. If it is correctly classified, then alpha will be 0. So, here for this alpha will be 0 and xi will be also be 0, and this is nothing but inequality hold. Okay. Now, if you after you come to pattern number 2, for pattern number 2, of course, it is correctly classified. So, xi 2 will be 0, and what about alpha 2? Alpha 2 will lie between 0 and c, because it lies on the bounding hyperplane. It is nothing but free support vector. Now, if you go to pattern number 3, pattern number 3 is for +1 class and lies on other side. Okay. So, this is not correctly classified. For this, xi will be greater than 1 and alpha will be c. If you go to pattern number 4, for pattern number 4, this is in this side. So, for this is basically xi will be between 0 and 1, more than equal to 0, less than 1, and alpha is basically c for this particular pattern. Now, if you come to pattern number 5, now pattern number 5 is also in that zone, but it is in this side of this plane, this side. So, that means alpha is c for this and xi is between 0 and 1. Okay. Now, if you come to 6, for 6 it is correctly classified, lies on the bounding plane. So, that means alpha will be 0 and c will be 0, alpha will be 0 and xi will be 0 for this, and this is nothing but free support vector. And if you come to pattern number 7, for pattern number 7, this is correctly classified. So, but it is not on the boundary. So, alpha will be c, alpha will be 0, alpha will be 0 and xi will be 0. Now, for this pattern, this belongs to basically this class -1 class, but it is here. So, for this xi will be greater than 1 and alpha will be c. So, in this way we can analyze if we are having a two patterns, that by simply seeing a pattern we can see that it is a free support vector, or it is correctly classified, or it is misclassified. So, this is basically the analysis of whatever I have discussed here. Now, the dual of the problem, as I already told you, the dual is simply maximizing the Lagrange function, okay, subject to the constraints. So, constraint basically come from here, this is a constraint. Okay. Now, this is Lagrange, maximizing this function Lagrange. So, you simply substitute w of this given by this expression here. Okay. So, what we obtain, this is two w's are here, so there will be two summation, one for I, other for j, and here also the two summations. So, plus half minus 1 will give minus half, as we have in hard margin classifier, the same concept will work here. So, on simplifying this expression, after substituting all this, after using all these expressions, we get the dual as this problem. So, again it is easy to use the dual problem, computationally easy to use a dual problem rather than using the primal problem as well. So, after solving this dual problem, we will obtain w bar and b bar. So, w bar can be obtained from this equation, you can see from this equation w bar can be obtained. Once you obtain alpha bar, so w bar you can obtain from this equation. Now, how to obtain b bar? So, b bar can be obtained if you go to this KKT conditions, see KKT condition number 5. So, if you see the KKT condition number 5, from 5 what we obtain? 5 implies alpha I times 1 minus xi minus di w transpose xi minus b is equal to 0 for all I. Okay. This is by this equation number 5. So, for some pattern xi, suppose alpha I is between 0 and C, then of course xi will be 0 as we have already discussed. So, xi will be 0 and alpha I between 0 and C. So, this expression implies, so hence it is 1 minus di w transpose xi minus b will be equal to 0. So, that means di w transpose xi minus b equal to 1. You multiply di both the sides. So, it is di square w transpose xi minus b equal to di. Now, di is either plus 1 or minus 1. So, di square will be always plus 1. So, this implies w transpose xi minus b equal to di. So, this implies b is nothing but w transpose xi minus di for that pattern for which alpha is between 0 and. So, in this way we can find b bar. So, this is an optimal b or b bar. Okay. So, we can find b bar from here. Now, let us discuss one example based on this. Now, we are having two classes here minus 1 and plus 1. Okay. We are having 1, 2, 3, 4, 5 patterns of this square, 5 patterns of minus 1 class and 5 patterns of plus 1 class. So, of course, these two classes are not linearly separable. So, how can we find out soft margin classifier? So, we can construct an equivalent quadratic optimization problem which will not only maximize the margin, but also minimize the misclassification error. So, we will use the help of the same optimization model which we have discussed here, this SP model. So, we will construct the SP model for this given example, we will solve it and find out the best possible soft margin classifier. Okay. So, how we can formulate? So, formulation is quite easy. What will be objective function? So, patterns are in R2. So, it will be 1 by 2 times W1 square plus W2 square plus C times sum of misclassification errors. How many patterns? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, there will be 10 number of 10 xi xi1 plus xi2 up to xi10. So, that will be the objective function of this problem. I have taken C equal to 1. I am giving weightage equal weightage to both the objectives. Okay. So, this I have taken. Now, of course, these patterns are correctly classified. For these patterns xi will automatically come out to be 0, not for this pattern, not for this pattern, and of course, for these 4 patterns also xi will automatically comes out to be 0 because they are correctly classified. Okay. Now, what are the constraints? For constraint, suppose we are having the first pattern 2 and 1. So, it will be minus of 2 W1 minus W2 okay, plus B plus xi1 greater than or equal to 1 from the constraint of SP model. And similarly, we can construct all the 10 constraint of this problem, okay, where xi I are non-negative for all I, W1, W2 and B are unrestricted in sign. So, this is the equivalent SP model or the soft margin classifier problem of the given numerical example. So, after solving this problem by using any solver, we get back to this as an 0.5 times x1 plus 0.5 times x2 equal to 3.5, which is the class or soft margin classifier we are having. These two are the bounding planes. This is 2.5 right hand side minus 1, B minus 1, this is B plus 1, these two are the bounding planes. So, in this way we can find a soft margin classifier of the problem. Not only this is the problem which I have used SP model as such. We can also use the dual approach, the dual model. This is a dual model which we have formulated, which we can also use the dual model to find out the corresponding soft margin classifier. So, in this way we have seen that if the patterns are not linearly separable, then also we can find out a classifier which not only maximize the margin, but also minimize the misclassification error. The model we can simply formulate the quadratic programming problem, or we can use the KKT conditions to find out the dual of the given soft margin classifier problem. Thank you.